So this lovely picture here is a picture that was taken 2 years ago, and it's an image of a Vulcan petawatt laser plasma interaction. So petawatts, 10 to the 15 watts. This laser is focused to about 5 microns, which is a fraction of a human hair, and it imparts energy onto the target that's sitting there. So what you're actually looking at is not the laser at all, because it's firing but you can't see it because it's infrared. Also there's an infrared filter so we don't zap the camera. The camera is looking from above, okay? So it's a plan view of the experiment. So the laser's coming in from this side, so it's coming in from the left, interacting with the target. And then you can see a lot of green light. And basically what happens is when the laser interacts with that target, some of that laser is actually re-emitted as harmonics of the original laser. So we can see second harmonic here because that's second harmonic of our infrared laser, which is 1053 nanometers. And then you can see some emission out of the back of the target. There's some protons coming out of the back of the target and they're traveling out. And we've got a stack of radiochromic film, which is what we use to detect the protons. And they're actually ionizing the aluminium foil that's covering the radiochromic film. And that's producing a secondary plasma, which is what you can see on the far right-hand side of the monitor. And now all of the stuff that you can kind of vaguely see around it are diagnostics that we use pointing at the laser plasma interaction so that we can understand what's going on. So you can see a funny kind of out of focus tip coming in there. That's an X-ray pinhole camera, and what that's looking at is the X-ray emission from the rear side of the target. So I'll clarify what we mean by rear side. It's the opposite side to where the laser's interacting. So what that's showing is how the energy is being transported and what's happening at the rear side, so we can kind of understand the size of the emission region, for example. Because this was an experiment that was actually looking at targets which manipulate the very hot electrons that are produced at the front which diverge, and these targets are basically designed to try and control the flow of these electrons so that they're not diverging so much. So we'd be using that X-ray pinhole camera to look at the heated region on the back and see if it was changing between control targets and these special targets. I'm very much in the business of producing extremely hot plasmas of temperatures of tens of millions of degrees. But there are some other people that sit at this institute who produce sort of low temperature plasmas. And people often ask, what is low temperature? Now, these plasmas, basically in plasma physics, you can have the concept of, the electrons having a different temperature to the ions. And in low temperature plasmas, you can have a very small number of electrons that are quite energetic and, satisfy the criteria for what a plasma does. And yet you can still have reactive species present in that as well. So, they're the kind of temperatures which you could fire it at a person, for example. So what these low temperature plasmas typically tend to be used for is a huge range of things. So for example, you can use them to manufacture computer chips, for example. There's some work going on at the Institute to understand how to make those better. And also then there are sort of biomedical applications like treating prostate cancer, for example, or disrupting bacterial biofilms, so sort of, antibiotic substitute for, clearing up infections. So bacterial biofilms, for example, are implicated in chronic wounds, and being able to disrupt them and, clear them up, would help chronic wounds to heal, for example. So there's a lot of interesting science involved in low temperature plasmas that involve a huge amount of chemistry, which you just don't get in really high temperature plasmas because they're fully ionized.